This question is about amines, an incomplete equation for step 1 in the reaction between bromoethane and an amine is shown. Complete the equation. In step 2 of this reaction, the product of step 1 forms a secondary amine. Name the secondary amine formed. So we're going to complete the equation. If you have a look, here's the ethyl part that came from the bromoethane. So what we're looking to do is say what this bit is, which is a CH3 with an NH2, so methylamine. We now need to name the secondary amine that would form. So what would happen next is one of these hydrogens would fall off. I'm not going to keep that on there though, because I don't want to make my equation incorrect. But one of the hydrogens would fall off, leaving me with one. The longest carbon chain containing the amine functional group is now this bit, so it is a longer chain. It's now ethylamine, and it has got a methyl group attached to the nitrogen, so it is N-methylethylamine. CH3, CHBr, CH2, CH3, so 2-bromopropane, reacts with ammonia. Draw the skeletal formula of the major product when we use an excess of ammonia. When you use an excess of ammonia, further substitution is stopped and you just make the primary amine. So we would make the 2-amino butane, or if you wanted to name it using its IUPAC name, 1-methylpropylamine. What if we use excess of the halogenoalkane? So when you use excess of the halogenoalkane, the nitrogen becomes substituted until it forms a quaternary ammonium ion, and these sticks are going to attach to this part of the butane chain where the Br was. So we got a 1 off one side and a 2 off the other side. 1. Okay, 1. So we're attaching that butyl via the second carbon to a quaternary ammonium salt, and we would get a floating Br- ion nearby. Figure 3 shows a 2-step synthesis to make amine G. Complete figure 3 by drawing the mechanism for step 1 and the displayed formula of amine G. Okay, so just double checking that none of it relates to the previous part. No, we've not mentioned anything. So we're making an amine. We seem to be putting a nitrile group on. So we're making an amine. We've got a halogen here. So we must have started with a halogenoalkane. So we've got a C with 2 CH3s. I'm going to draw it out like this. And a H. The halogen would have been here where the CN now is. So the Cn minus from KCN is going to attack the delta plus carbon and kick out the Br. That is then going to be reduced using hydrogen and a nickel catalyst. And so the CH, that part stays the same, but we get CH2, NH2. We're reducing both parts. Oh, and it said give the displayed formula, so we'll correct that. So we read the question carefully. We're going to display everything. So this C with 1H has got 2 CH3s attached. Then we had the C that was over the Cn, that became a CH2. Then we had the N, that became an NH2. Figure 4 shows 2 amines, P and Q. Explain why P is a stronger base than Q. So these are bases because the lone pair is able to accept a proton. Now, if P is a stronger base, and without really understanding our explanation, we need to be able to write that the lone pair on N in P is more able, this makes it a stronger base, to accept H plus than the lone pair on N in Q. And why is that the case? And it's to do with the number of alkyl groups, the positive inductive effect of alkyl groups, as P has more alkyl groups which have a positive inductive effect increasing electron density on N.